Hello, welcome to my Module 3 presentation. Today, I'm interested in seeing if I can predict the probability of someone being a serial killer or not being a serial killer. I'm taking a behavioral profiling class and was given a list of variables and participants, and it's my job to identify the odds that these individuals will be or will not be a serial killer based on the region of the United States in which they were born and their score on a test that measures levels of psychopathy. So following Friedman's advice, we need to know the connection between the models that we're presenting and the phenomena that we're interested in studying. So we will define our variables and make sure they are distributed how we would want them to be distributed. So our first variable here is our outcome variable. So it's important to note this is a binary variable with zeros and ones as the values, 0 being no, they're not a serial killer, 1 being they are a serial killer. Then we have our categorical predictor, which this is the region of the United States in which the individual was born and raised. And you can see here that we have uneven groups. So we have 1 being the Western region, 2 Northeast, 3 Southwest, 4 Midwest, and 5 Southeast. So we have different number of individuals per each group for this sample. And then for our continuous predictor, this is the score that an individual received on the Tri-Arctic psychopathy measurement scale. And we can see this is pretty normally distributed. So for the purpose of this presentation, we'll be including an interaction in our model to determine if it helps explain our phenomena of interest, to see if the probability of an individual is a serial killer or not, and if there's unique combined effect of our two predictors, region and psychopath score, that explain more of our outcome than they would solely as main effects. So that being said, our variables will be centered to allow for interpretation of the interaction and mitigate concerns of scaling. So here at the bottom, this is after scaling. So this is just essential multilinearity that we have left that we cannot get rid of. So we're going to go ahead and model this as a linear regression because that's what we're accustomed to see if this fits. So it's a little different than what we're used to. And it's making me think we may have to consider another way of modeling our data because it seems we have a misspecified model, as you can see here in the scale location plot. So I'm leaning towards using logistical regression because we do have a binary outcome, and I'm interested in the probability of, and this data doesn't typically show a linear relationship. And I'm particularly interested in the likelihood of someone being a serial killer or not, given their psychopath score and the region where they grew up. So we're interested in predicting a qualitative response. And as Press and Wilson say in their article, logistic regression is preferable when you have a qualitative data. And logistic regression measures the relationship between a categorical dependent variable, which we have as 0 and 1, and one or more independent variables by estimating the probabilities using logistic functions. So we go ahead and plot that, and we have these diagnostic plots, and you can see this fits our data better. We do have one outlier, but it doesn't seem too concerning for this model, but this fits our data better than linear regression did. So what's the main difference between linear versus logistic regression? Well, they're both specific types of the general linear model. Linear assumes that your dependent variable is continuous and it can be any number on your axis, and it assumes that it's quantitative. Well, logistic, the values of your dependent variable are confined to the probability values between 0 and 1. And this is what we see in our outcome variable and the data collected for it. It's binary and it's not continuous. And it's also qualitative, as we noted, is another part of logistical regression. So instead of predicting values as you would in linear regression, logistic regression estimates the odds of a certain event occurring, which is what we're interested in. The odds of someone is a serial killer or not. So although both are under the general linear model, they do not necessarily share all of the same assumptions either. In logistic regression, the Y variable does not need to be normally distributed as it does in linear regression, which we saw in our histogram as well. It wasn't normally distributed. But both of them do worry about multilinearity. They want to limit outliers, and you have to have a large enough sample size in order to continue with the model. So our next issue we have to face are our coding decisions. So this is the transformation of our categorical variables. We do this so that we can represent how the data will be recoded and created. So each prediction will be entered into the model in a certain way depending on the type of coding we choose. So choosing a type of coding depends on the questions that you're trying to answer and the categories that you have. So our question is, are there certain regions that someone is from that have a higher probability of producing a serial killer than the West? Because that's what we're going to make our reference group, because more serial killers are typically from California, which is in the Western region of the United States. So we could choose dummy coding, which is when we code ones and zeros for our different categories, and the differences between our base group and each other group are tested, and the 0 is explicit. But we can also choose effects coding. So this is when we produce contrast between levels, but the 0 is implied between the contrast, so your 0 is implicit. And within that, we utilize grand means to our other means. And we have weighted effects coding and unweighted effects coding. Unweighted effects coding still compare groups to our grand means, but we need even cell sizes across our group. So the same amount of participants in each group. While weighted effects, the cell sizes are allowed to be different because we're using weighted based groups. So the weights represent the changes in frequency for each of our effects. So each group compared to our reference group. And then we have contrast, which allow you to test multiple hypotheses at once. And here you're making a direct and relevant comparisons, and the codes need to sum to 0. There's also nonsense coding, but that's a little complicated for the prospect of this presentation, and so we will not be talking about it. So the coding I've chosen is weighted effects coding. And we picked this because our 0 is meaningful. Since we're going to have an interaction, we have to center our variables. And if we center a dummy coded variable, that group that's 0 will no longer be meaningful. So we chose effects coding, and we specifically chose weighted effects because we have a different number of cell sizes per group. So once we've implemented this coding, our categorical variable is now centered. And so our comparison group will be the region of the West, as I stated, against our other regions. So does the mean we observe for each region differ from the weighted mean of our reference group? So given that, we're given this logistic model output. It's important to note we are viewing our log odds here in our estimates, and we can see that we have significant main effects for psychopath and regions 2 and 4. So it's important to note here for region, these are deviations from the grand mean, as we stated. So this is the unique variance accounted for by that specific region, excluding the other regions. So region 2, you see, has a negative relationship with outcome, while region 4 has a positive relationship with outcome, which will be important to note when we get to interpretability. You can also see we don't have any significant interactions. So this is telling me that region does not appear to significantly moderate the relationship between psychopath score and if they are a serial killer. So more variance is not explained by our interactions. So all of the variance need to be explained in our outcome is taken by our main effects, and there's nothing left for an interaction to explain. So to get into our model, our estimates here are logit coefficients, and these are estimates that tell you about the relationship between our independent variable and the dependent variable, where the dependent variable is on a logit scale. Now, these log odds are really difficult to interpret, so we'll save the interpretation until we transform these into odds ratios. And you can see also we have our standard error, which are typically accustomed to seeing in our linear regression. But the difference here is we see we have a z-value where a t-value typically is. Now this is, in logistical regression, the z-value replaces the t-value, and this is part of our hypothesis testing, but it operates the same. So it's still generated from taking our coefficient and dividing that by our standard error, and still informs our p-value, which is still at 0.05 and tells us we are able to reject our null hypothesis of there being no relationship. And we can do that, we see for psychopath score and region 2 and region 4, but nothing else. You also can see we have deviances here at the bottom, which is the goodness of fit of our model. So the null deviance and the residual deviance are used to test whether the independent variables provide statistical significant explanations. So you can see that our residual deviance is lower, so our predictors help explain more of our model than just the null deviance. But it didn't go down by a lot, so although we are explaining more, maybe we could do more to explain more in the future. Then you see here we have our AIC, which is useful for comparing models, and it operates similar to how an adjusted R-square would in a linear model, because it accounts for the number of variables used compared to the number of observations. We also have our Fisher score here at the bottom as well, and this is the number of iterations it takes to fit our models. Because our model is not linear, it's fit based on guesses or maximum likelihoods. So it's how many times our model was improved using different estimates before it stopped, and this is the results we're given, which was 5. So now we'll go ahead and move to odds ratios for our interpretability of what our model is actually telling us. So this represents the constant effect of our predictor on the likelihood that one outcome will occur, so being a serial killer or not. So the odds are easier to interpret, and it's just the exponential value of our estimate that we previously saw. So the way to see if the value is significant is if the 1 is considered or added in between or is present between our confidence intervals. If the 1 is present, you do not have significant results. So you can see here we have the same significant results as we did on our other output. So for continuous variable, this is telling me the average effect of the psychopath score increased the odds of being a serial killer by a factor of 1.16, given the average reported region. So in other words, the odds of being a serial killer increased by 16% for a unit increase in psychopath score. Then for our region predictors, the odds of a person having grown up in the Northeast region of the US, because that's region 2, of being a serial killer are 0.44 times less than the odds of a person in the Western US. So the odds of being a serial killer decrease by 56% for an individual that lives in the Northeast compared to the West. And then the odds of a person having grown up in the Midwest region of the US being a serial killer are 1.8 times greater than the odds of a person in the Western region. So the odds of being a serial killer increase by 80% for an individual that lives in the Midwest compared to the West. And this is when the positive and negatives of our estimate come into play for our interpretability. So you can also see this in our plot. On our y-axis is our predicted probability for our outcome. So 0 to 0.5 representing 0, and that being not a serial killer, 0.5 to 1 representing 1, so saying yes to being a serial killer. And you can find the score on the psychopath test on the x-axis, and then go up to the line that matches the region that they're in. You can see that here on the legend, regions 1 through 5 and the colors associated with that. And so you find the psychopath score, find the line that matches and go across, and it tells you where this individual falls on our predictability scale. So you can see that when individuals score about 125 on the psychopath scale, it really doesn't matter the region they're in. They still have a high probability of being a serial killer. And this might have to do with the fact that we didn't see any interactions in our model between region and psychopath in predicting our outcome. So we can also compare this to our linear model just to see the differences. And we can see that our estimated values decreased a lot from linear to logistic. So perhaps they did that because we're using logit functions with logistic regression and that we don't use in linear regression. So these aren't bound to be the same. However, you can see, other than the intercept, that the same main effects are significant in our linear model and our logistic model, which is just important to note. So we're still saying the same things are significant for our model. And again, you note the difference in Z's and T's, but we're still interpreting them in a similar way. So to really compare our two models, we can use confusion matrices. So these compare the actual outcomes to our predicted outcomes. So it tells you how many predictions were yes or no compared to reality. So it compares our prediction to our reality. So which model is comparing more? So I did this for logistic and for our linear models to compare if one was better or told us more than the other. So they're actually pretty close in terms of what we were able to predict versus what we falsely predicted. And so we seem to be slightly less strict in our logistic regression because we have less false negatives, but one more false positive. So it's telling me we don't really lose or gain anything from using logistic regression versus linear, but we want to use logistic because of the structure of our dependent variable and the questions we're asking. So we're not actually explaining that much more with logistic regression versus linear or in our predictability power, but it's fitting our model better, as we could see with our diagnostic plots. So just to have a model check and run our example of a person, we're taking Jeffrey. Jeffrey was born in region 4 of the United States. He was born in the Midwest, you can see here on the map. And he had a psychopath score of 150. So you can see on the graph here, the probability of him being serial killer is yes, and it's actually quite high. So actually, when looking into the future, we saw that this was Jeffrey Dahmer, and Jeffrey Dahmer is a known serial killer. So that shows the predictability power of our model. And actually for this data, known serial killers were added in to test our model's predictability. So it checks out that way. So overall, this is telling me our model does have predictability power, although I think we could still add more to it. So we could do this by perhaps having other regression models model the relationships we're interested in. Perhaps they could explain the phenomena better. We could also have different variables that could have higher predictability power. So perhaps not region or psychopathy score, maybe we could use different variables that actually add more to our study, and that would just have to go with understanding our phenomena a little bit more. We also worry about having false positives and false negatives. So our false positives is when we predicted, yes, they were a serial killer, but they not, which is kind of bad because that's us assigning someone a serial killer when they're not. So that's a false conviction. And then we have false negatives, which is when we predict that they're not a serial killer, but they actually are, which is extra scary because that means we're letting serial killers loose on the street, and we don't want to do that. So although we seem to get a lot right, as you can see in our confusion matrix here with our true positives and our true negatives, we still want to do better with our model because this isn't really a odds that you want to get wrong of the odds someone's a serial killer, they're not. You want to be pretty accurate with that. So I think we could always improve our model. But thank you very much.